Uno, dos. Uno, dos. Uno, dos.
Okay. Good morning. Welcome to the second day of the Inqua Mare workshop. I'm so sorry I'm a little bit without sound. Okay, we have some announcements. Please, Jean-Paul, la siguiente, por favor. Sí, okay, okay. First of all, thank you. The social dinner is on República Cervecera. It's close to here, next to the Rotonda de la Bandera. It's pretty close to here, so we can give you the position. And okay, you will need to pay for your own this dinner, so you can bring whatever you want. Okay, it's at 7 p.m. All right, and then the other things.
We lost probably one, but we'll say it to you in any case. So the other announcement is the same of yesterday. So please go join Mighty Networks, because you will find posters that are also from people who are only online. So it would be nice if you go on Mighty Networks and you go in the feed, which is here, and you will see all the posters. Some of them have been uploaded by me, but you can still search for them by searching the surname of the first author. So you will find them, you can open them, and please comment them so that you can interact with the author. The other thing I would like to say is that we will have a group photo just before lunch, so please don't leave, don't run away for your food. And there was another announcement. Let me see. Should be the first one. Oh, there it is. Okay, the most important.
Okay, some changes. We have some misses presentation, so we changed the speed talk presentation by Stephanie just before the last coffee break. So we can go into the posters with our coffee and stay there a little bit more. And the campus tour will be tomorrow instead of today, okay? So we're staying here and we will going to make a little trip around. Thank you. And we can start right now. I leave you with our third of today, Eddie.
Thank you very much, Viviana. Good morning, everyone. Jean-Paul. The next presenter is Patricia Siveri. She's online.
Yes.
Okay, let me introduce you to Patricia. Patricia Siveri. Okay, go.
Yes. Can I start?
Okay. Patricia, she is from the Universitat Autónoma de Barcelona, Catalan Institute for Research and Advanced Studies. Patricia Siveri is a research professor at the Autonomous University of Barcelona, where she is a professor at Institute of Science and Environmental Technology. And she was the scientific director of the ICTA and UAB from 2015 to 2020. Her research includes global environmental change on marine system, ecology, and biochemistry. With her work, she's linking to CO2 dynamics, climate, marine, and coastal systems, and their societal relevance. She leads the METSEA project, an international research initiative that studies the impact of the Mediterranean seas, warming, acidification on crucial species and ecosystems in the area. Thank you, Patricia, and we can start with Patricia.
Thank you very much. Can you hear me okay?
Yep.
Yeah? Okay. I will just share my screen. But before sharing my screen, I actually want to thank you very much for the kind invitation. And I'm sorry not to be there, first of all, because I like, of course, to share the conference with you in person, but also because I was in Costa Rica last year for my holidays, and I really love Costa Rica. It's a beautiful place and also very nice people. So I hope I have the opportunity to come back. And I'm here today to present some of the results from my group in Barcelona. Can you see the slides okay? Yeah? Okay, great. So the topic of the presentation today is about anthropogenic carbon dioxide, and how this carbon dioxide is changing.
Patricia, I'm sorry. We have a little problem because you are sharing, I think, the second screen.
Oh, okay. Let me see if you can see it like a full screen. 1 second. I'm trying to swap display. 1 moment. Like this?
Okay, yeah, it's pretty good.
Full
Thank
screen?
you. Yeah.
Okay, great. So actually, since the topic is anthropogenic carbon dioxide, the first slide that I wanted to show you is about annual carbon emissions. And you see that the carbon dioxide emissions from 1750 to today, I'm sure you are very familiar with this kind of plots, has been drastically accelerated and actually is continuing to grow very rapidly from, second and to the pointer. Yeah, so from 1950, you see this drastic acceleration, and then also from the 90s, even faster. It's going, and actually last year in 2022, we almost reached, 2 years ago, in 22, we reached almost 37 billion tons of carbon dioxide per year. And of this carbon dioxide that we are emitting, about 50% is actually staying and accumulates in the atmosphere, and the other 50% is sequestered by natural processes on land and also by the ocean. And since the focus of my presentation is the ocean in relation to this rapid accumulation of carbon dioxide, the key processes that we talk about today, there are mainly two, but here I will also show in the three of them. So one is about the ocean warming. In fact, the ocean is trapping most of the heat generated by climate change. And we know that actually changes were very small in terms of temperature until 1980. But that's from 1980, this amount of heat that was stored in the ocean began to steadily increase. And then from 1990, really this increase was accelerated and is calculated about, estimated about 93% of all this heat is actually ending in the ocean. And the other process that is also linked to warming and this accumulation that you see here of carbon dioxide is the warming is actually causing the ocean the ocean is losing oxygen, and there are two main reasons that they are losing oxygen. One is because warmer seawater can hold less gas, including oxygen, and also that there is a stratification, more enhanced stratification that of course cause less mixing and less oxygen that you can reach the deeper depth. Another process is also very well known is ocean acidification, and this anthropogenic carbon that so is also causing acidification is a process that describes the increase in hydrogen ion concentration and decrease in calcium carbonate mineral saturation state. So these three processes here, what you see is the global main projection of upper ocean impact drivers. This is also a modeling exercise. What you see is a trend from 1900 to the end of the century, 2100, and you see the anomaly in the three processes that I mentioned. So the warming, the delta sea surface temperature. In black here you see the historical data, and here with different color the projections of warming, of sea surface temperature warming, depending on the CO2 emission scenario. So the worst here is in red, and you see it's about 4 degrees of mean global temperature increase. For the pH, you see the same thing here. So the historical data, and then the worst scenarios, the 8.5 CO2 emission scenario, iteration minus 0.5 unit of pH. And finally, here is the oxygen level, oxygen concentration. It is also supposed to decrease. Here is in millimole per cubic meters, and is supposed to decrease also with an anomaly of minus 15. So these are major changes that the ocean is experiencing already, and is supposed to experience even more in the next decade. What I wanted to address in my presentation are some key questions that are still open. Is about how the ocean warming is affecting plankton productivity. Of course, we have some idea, but I will show you some results of this. Also, how ocean acidification is modulating biogenic acidification, and not only, and how perturbation of ocean carbonate system is actually can influence the pelagic carbonate production and also a shallow dissolution in relation also to ocean warming and acidification impact. Just a second, I had a mistake in the room. And the target region that I'm gonna focus on, the mainly Mediterranean Sea, and the other two regions are the Arctic Sea and the North Pacific Ocean. So here is my first question that I want to address. So how the ocean warming is affecting plankton productivity. Here you see these familiar plots that I just showed you before, but now they are for nitrates and also for primary productions. So on this side here, you see the upper photic zone, so the 0 to 100 meter projection for the nitrate. Here in dark again, the historical data, and in red, the overall decrease is projected for the nitrate in the upper ocean. But then when we look at that integrated net primary production, we see no very much changes happening until today. And then from a slight decrease, I would say, in the last few decades. And then for the projections, you see overall weak decrease in primary production. But what I wanted to highlight here in this plot is that there is a very large uncertainty in the projection of primary production. So there is really a need for better understanding primary production dynamics at the local and at the regional level in order to understand really what's happening to primary production in different sites. So this was our motivations. And before going into some results, also wanted to share with you the model groups that we are using for this type of study. They are pelagic calcifiers. And you are very familiar now with these pelagic calcifiers because there were a very nice talk yesterday introducing and using this planktonic foraminifera and also cocolithophorus here, this abundant calcareous phytoplankton. And on the right here you see the theropods that are basically swimming gastropods, swimming planktonic mollusks. And they become very much studied lately because for ocean acidification, they are basically planktonic organisms that offer to be like a sentinel of ocean acidification. So they are very sensitive to changing carbonate chemistry because their shell is made of aragonite. It is a very much weaker, we say, mineral of calcium carbonate mineral compared to calcite. So important points related to these groups is that are in general at the base of the food web. So it's phytoplankton, zooplankton. So when we are impacting these organisms, then we can also understand a bit more if there are consequences on the food web. So they are important for understanding a bit better the dynamics of the food webs. And also for my group and for us, is important because we can use this group targeting responses at different temporal scales. So we can basically grow this different organism in the laboratory. We can test the response of this organism as specific drivers of forcing, like temperature or, for example, acidifications. And then we can look at the physiological response, usually with just one species, one species or a couple of species. And this is a temporal scale of a weeks. And then we can also do mesocosm, maybe in months. But the important thing is also that they have a great, as you all know, sedimentary record. And for the time frame that we are addressing, so basically the human time scale, we can address decadal variability and also centennial variability. So when you have the proper sedimentary record, we can also address questions related to this type of variability. Also, we can offer a pre-industrial baseline state that is impossible, of course, when we run just a lab experiment. And we go back to this later. They are a main player for carbonate cycling, and also they are very sensitive to the environmental change, including for seawater carbonate chemistry that we know is changing quite rapidly at the moment under high CO2. So the first case study is in the Mediterranean Sea. If you were listening yesterday, it was a really interesting talk by Isabel Cacho. She did a very nice introduction about the oceanography of the Mediterranean Sea. So here what I wanted to highlight are just some key points. That the Mediterranean is known to be a climate change hotspot and is very much under climate change even at the moment. And in the ocean warming that is happening is actually above global average, so about 20% above global average in the warming. Also, in terms of ocean acidification, Mediterranean is a bit different than the open ocean because there's relatively high alkalinity. There is a gradient from Gibraltar to the Eastern Mediterranean in terms of alkalinity, with higher alkalinity in the Eastern Mediterranean. But the fact that there's high alkalinity means that, of course, it's buffering ocean acidification a bit more, but also it's trapping more anthropogenic carbon at the surface. So as the capability has very high, actually, concentration of anthropogenic carbon at the surface. And because the circulation here is relatively fast, it's very dynamic, and the overturning circulation is in the order of 80 to 100 years, the anthropogenic carbon that, of course, is concentrated at the surface has already penetrated the entire Mediterranean from the surface to the deep. Also, there is a nice place to work on ocean deoxygenation, not so much because now there is deoxygenation, but because there were time interval in the past that they were experienced anoxia or deoxygenations, and amplify the record of environmental signal, and you can find nice temporal resolution sediment records. So the first record that I wanted to show you is from Sven Palak, that finished last year his PhD at ICTA, and one of the questions that he answered in his PhD was this question about plankton productivity in the Mediterranean Sea. And he ran many proxies. We have many proxies that were run in these two cores, one in the Catalan Balearic Sea, that you see here, and one in red here, very close to Gibraltar, the Alboran Sea. And these are the two main sites for this study. What you see here is, and they have a high resolution core spanning both of them the middle-level climate anomaly until the industrial era, so this time interval. And also what you see here, the sea surface temperature that I would like to show you, and the CO2, atmospheric CO2 concentration. So first of all, one thing that you see when you look at pre-industrial time in terms of sea surface temperature, that we have some variability that is a natural variability of climate change, and we see that this variability you see more not only in sea surface temperature but also in productivity. They are mainly modulated by the North Atlantic oscillation modes, and so we assume that during this time was a quite strong vertical circulations, and so there was very low thermal stratifications. Then if we move to the industrial period here, so here is this amplified, you see this amplified signal of sea surface temperature for the two records in blue and in red. And then also what is plotted here is the annual sea surface temperature and the standardized sea surface temperature anomaly that is obtained by instrumental data. And again, here you see the CO2 emission, the CO2 concentration. So you see here again the warming that is happening in these two sites. Then in terms of primary production, or plankton productions, I would say, we use different proxies. And what I show you here is the proxy for surface productivity based on relative abundance of species of foraminifera. So different species for different sites, but mainly is inflata, truncatulinoides, and bulloides that are used in this study. And if you compare here the pre-industrial time, you see so these are the data that are shown, and you see pre-industrial is mainly modulated by decreasing and increasing in phases of the North Atlantic oscillation mode on multi-decadal timescales. And also you see here the standardized total plankton foraminifera test accumulation rate at the Alboran and the Balearic Sea. So for the pre-industrial time, you see a slight decrease and also variability as well. And then when we move to the industrial time, we see in both sides a decrease using this proxy, a decrease in productivity. So in terms of anthropogenic warming, we see a decreasing trend of both solar productivity that is seems to be linked with stratification, and also offer like a nice way to get a baseline for pre-industrial calcifying plankton community. And one of the interpretation, of course, of this stratification is the weakening the northwesterly winds and the deep water formation that is lowering the Atlantic inflow and is reducing the upwelling, increasing then the relative abundance of inflata, for example, over the bulloides. So the other question that I wanted to answer was about ocean acidification in sedimentary record and also modulating pelagic calcifiers. I would say that most of the knowledge that we have in terms of ocean acidification impact on species and on different type of groups of organisms comes from laboratory experiment. So laboratory experiment mimicking, of course, different scenarios of acidification are absolutely very important for understanding the response of biomineralization, the physiological response but of course is not realistic, a laboratory experiment compared to the natural systems. So there are now more and more experiments addressing multi-stressors, or mesocosm experiments addressing multi-stressor, or asking different questions. So here, for example, we did a mesocosm addressing warming and acidification in the Eastern Mediterranean, and showing that actually warming is absolutely detrimental for many calcifiers, because particularly in the Eastern Mediterranean, temperature are very, very well above the optimum temperature of this organism at the surface. Also, another interesting study we did that was a bit different than just looking at the particular organic carbon as a response to warming and acidification, but we also look at the nutritional response of Coccolithophores as a food at the base of the food web. And we saw that there was a slight increase of particular organic carbon, but then looking at in detail the lipids, we could see that actually the nutritional quality of these lipids was actually worse at the high temperature nice CO2. But now we go back to the sedimentary record, and we go back to the foraminifera, and we go back also to the Mediterranean, and we did a study addressing this question related to acidification and biogenic calcifications. And we wanted to know also if there were any sign of change in both acidification and anthropogenic carbon sequestration in the sediment, as well as calcification. So what we have done, here is, so we have these three cores. We are familiar now with the core in the Gibraltar, in the Alboran Sea, and the one in the Balearic Catalan Sea. And then we had an additional core in the Strait of Sicily, and basically what you see here, some of the key proxies that we use. One is the delta C13. You will see results that has been used to trace anthropogenic carbon in the core, in the calcite of the foraminifera, in fact. One is morphometrics of foraminifera, and also to analyze the size normalized weight, and then finally the pH reconstruction based on boron isotopes on foraminifera shells. So I show you now some of the results from this study. So on top here again, you see the atmospheric CO2 concentration that is derived from measured and reconstructed records. And here you see the delta C13. So the delta C13 that is shown here is a generalized additive model that fit the three sites. And in order to standardize the delta C13 results that were basically from different species and different sites. And here you see the different things. So you see the standardized pH values estimates calculated through CO2 sys from the different sites. And also you see the pH reconstruction from boron isotopes from foraminifera shells. And finally here you see generalized additive models that fit the standardized size normalized weight for the different species and from the different sites. So when you look now at the pre-industrial, period, you see not very much is happening in terms of this proxy that we are looking, or the CO2 variations. And but then when we actually focus on the industrial period, we see something interesting. We see something related, for example, to the delta C13. We saw delta C13 that is becoming actually lighter in the different sites, and what we call it, this is a sign of what we call Suez effect, and it's because fossil fuels that is returned to the atmosphere through combustion is depleted in carbon-13 and carbon-14 compared to the atmospheric carbon dioxide. So this is something that is an indication of the carbon, or contaminated carbon, anthropogenic carbon in the core, and specifically in the foraminifera shells. And here you see this decrease in pH that started roughly in 1950 already. We have some indication of that, and similar to with the size normalized weight of the foraminifera, they are also decreasing. So we have strong indications here that acidifications started some already signed in the sedimentary record from 1950, and also they are modulating already the plankton foraminifera classifications. Then also we have indication of anthropogenic carbon in the sedimentary record, both from carbon isotopes and from boron isotopes. And also wanted to highlight that we have quite some high confidence in the result that we had, because there were different species and there were also different sites with quite different oceanographic setting in the Mediterranean, and we have this low variability assessment. Now we move away from the Mediterranean, we go to the Arctic briefly, and these are show some results from Griselda Anglata-Ortiz, that she just also finished her PhD at the University of Tromsø, and I co-supervised her thesis. And she did a similar approach in the Arctic, the one that I just showed you, and it's of course very different settings. Here, ice coverage is very important for understanding the biogeochemistry of the place and also understanding foraminifera and turtle distribution that she works on. She works mainly on water samples and plankton samples and sediment traps, but she also works on sediments, and I show you here some similar work that I've just shown you on the Mediterranean. So here we have two sites. This site is the North Barents Sea, and this is the Southern Barents Sea. And in the North Barents Sea here, you have almost permanent ice. I mean, you have a lot of ice coverage on this site and very corrosive water. And here you have, in the southern one, you have the influence of the branch of the North Atlantic currents, and you have higher concentration of calcium carbonate. I just want to show this from this record. and this is on this side, you see the Northern Barents Sea core record, and there are different data related to foraminifera. So you see foraminifera abundances, you see also the size distribution, and then you see the foraminifera calcium carbonate contributions in the core concentration. So here you have quite low carbonate and very little foraminifera record. But on this site, we were not sure about what to expect, because it was a southern site, was with the influence of the North Atlantic current that we know is actually increasing in this region. We were expecting maybe to see an increase of foraminifera productions, but in fact, what we could see more or less from the same time, from 1950 on, we see also a decrease from the industrial era to now. We see a decrease in foraminifera concentration. Sorry. No, I'm here. So foraminifera concentrations, and also a decrease in foraminifera carbonate. One of the thoughts that we have here is that possibly, of course, the rapid melting of sea ice in the regions causing a very strong that are significant for foraminifera productivity. So basically, this can be also causing a decrease in the productivity of in this region.
Patricia, I'm so sorry. We lost a little bit of your talk. The last minute, maybe the last slide. I think if you can repeat, please, because
okay.
we lost the connection. Just a few seconds.
Oh, okay. Where were you? Here? Oh, here. Were you here? So basically, the message that I want to deliver for this record was that so we have these two sites, one in the north and one in the south. So North Barents Sea, Southern Barents Sea, and this site here is interesting, particularly for us, because there were forams and there was carbonate, and we wanted to test the hypothesis that the enhanced North Atlantic current in the region would actually maybe enhance our productivity for foraminifera and in general. But what we could see here that we had a decrease, and we are having a decrease both in foraminifera and also so foraminifera concentration, and also on carbonate concentration related to foraminifera abundance. And the interpretation that we had for this decrease was that is increasing influx of North Atlantic because, of course, a rapid melting of sea ice and ice in general. and this melting of fresh water can cause high stratifications on the upper ocean, so impede the mixing of the upper ocean, so impeding the fertilization of the upper ocean, maybe where the foraminifera are living. This is just an hypothesis, and we have other proxies showing, of course, warming and also acidification. So the last topic, last results I wanted to show you is something quite different than what I've shown until now, also related to carbonate, also related to pelagic calcifiers. Now is in the North, we are in the North Pacific, so very different area. And also we are not in the sediment, we are in water. So these are water samples that were collected. So from Hawaii to Alaska, so we are crossing here the subpolar gyre, and then we are going to the subtropical gyre to the subpolar gyre. Also in color here, you see the particular inorganic carbon concentration in August, when this curve was happening, and you see this very large gradient also in carbonate productions. So one of the goals of this work was really to better characterize the carbonate production. Probably you know, but basically almost all carbonate that you find in the ocean is biomineralized, so is biologically produced. So we wanted to understand much more what are the organisms that calcify, that they are contributing to this carbonate. And also we have some indication from geochemical study that shallow dissolution can be a very important phenomenon or process happening. And this is also important, of course, because if you dissolve calcium carbonate, you are also input a lot of alkalinity. So you can also have a major impact on the alkalinity in the ocean. So remember now, the station 1 is the subtropical gyre, and the station 5 is in the north, because next plot I'm going to show you this result from this study. So this, as I said, this is 1 and this is 5 stations. So this is the north and south. And what you see here is an annual calcium carbonate productions that is being derived from the main calcifier that we quantify there. And so for blanket foraminifera, for coccolithophorus, and also pteropod and heteropods. So the total calcium carbonate production is shown here by these violent plots in the panels. And it's basically what you see here is the probability density of the estimate that is represented by the thickness of this shaded area. And the gray line shows the 68% and 95% confidence interval and non-normal distribution with the high tail on the upper estimate. Also what we did, we show here the total calcium carbonate, and with this color here, you see the estimated coccolithophorate carbonate, and you see that basically most of the coccolith calcium carbonate is basically building almost the total carbonate. So roughly 90% of the carbonate production is made by coccoliths. Of course, these are integrated values, so for the production layer. So we wanted also to make sure that these results were robust, and we compare with many different data. So for example, here in purple, I don't know if you see very well, but this band here is representing the theropod almond production that is derived a very large database. It's called Mare. And also here, what you see with this blue star are the estimate of the total productions calculated with the in situ pH and FCO2 measurement at the Papa station, and also with the other values here are from the North Pacific, calculated with alkalinity dissolved in organic carbon. So our values are actually within the range of this. And what are also the implications of this work is that we also saw not only that we could actually determine the different component that build up this large amount of calcium carbonate produced, but also we saw the large portion of this pelagic calcium carbonate is actually remineralized within the photic zone. And as I mentioned, this is important because this process is the one also that helps to regulate the sequestration of carbon dioxide in the upper ocean. And there are a lot of still open questions that we answer. For example, what are the anthropogenic warming and acidifications, how this anthropogenic warming and acidification is actually impacting the production of calcium carbonate at the regional or the global scale. We saw in general there is a decrease in production, but we still need to work a lot on this process of shallow remineralization because there's still a lot of unknown. There are some hypotheses, of course, why this is happening, because this water, of course, they are not undersaturated on calcium carbonate. And finally, some reflection about what I presented is that in general, what we see is the production of calcium carbonate is decreasing. And also we saw in general, and now we study that the carbonate mass is decreasing. And in general, the carbonate mass of the organism, the calcifier, of course, is very sensitive to change in the carbonate chemistry. Also, a reflection is that we really need to understand much more the alkalinity dynamics because it's so important for this uptake of carbon dioxide. And when you think about ocean alkalinization approach, then now is maybe the last several years, we are thinking to basically try to solve the problem of carbon emission with carbon removal. We need really to understand much more the natural alkalinization in shallow water that is not really fully understood. And finally, also, I wanted to, I don't have to convince you for sure, but I wanted to highlight the importance of sedimentary record also for this study, addressing the perturbation of the carbonate cycling. And because we can address multi-stressor, we can address community response. And I really see the strength of combining sedimentary record with the high resolution sedimentary record with lab experiment, observation, and mesocosm. And with this, I would like to thank you and my group, of course, and thank the workshop, and thanks for listening again.
Thank you very much, Patricia. I don't know if someone have any questions. No? Okay.
Hi, Patricia. I'm Caterina Morigi from University of Pisa. I have a question, a very specific question about foraminifera, of course. I saw in your graph that in the Arctic, if I remember well, the weight of the foraminifera decrease and the size remain constant, whereas in the Mediterranean decrease the size and the weight. Can you have a reason? Can you explain why there is a reason? So it means that in the Arctic the test became thinner, but the size remain the foraminifera remain the same size. And in Mediterranean decrease the size.
Yeah, that's an important information. Of course, usually when we, of course, evaluate the change in classification or classification mode, we look at the size normalized weight. So we look at change in size that can have ecological, of course, importance, but also we look at the change in size normalized weight, so the mass that is corrected by size. So the question about the Arctic, first of all, this is only one site, so that also can be one reason. One site versus like 3 sites, maybe not. Also, what we see in the Mediterranean that so the 3 sites are actually quite different in terms of oceanographic settings. As you know very well, the Mediterranean is general, is oligotrophic, but the Alboran Sea is not very oligotrophic, it's high productivity. So there's a lot of variability there that they can control the size. I mean, when we look at plankton foraminifera in the Mediterranean, we see a gradient from the Gibraltar to the Eastern Mediterranean, also in terms of size, and in terms, of course, of standing stock as well. So it just This fertilization can be one that is one side. One of the reasons is because one side also
my
straight.
question is because studying the
the
sapropel,
variability.
I studied the sapropel. I saw that, for example, Urbulina decrease during the sapropel. He has a thinner test, but the size remain almost equal or bigger than the Urbulina of pre-sapropel and post-sapropel. So when there is a warmer environment and an anoxic environment, Urbulina has less weight, so is weight less, but with a thinner test, and became a little bigger. So it's a little different from what you show. It's just my question that I have in my head about what happened in the sapropel in comparison with what happened now during the Anthropocenic time. So.
Yeah, what we are doing now is quite anomalous. So
yes.
I don't know if it's very reproducible.
Okay, yes. Thank you.
Thank you.
We have another questions or by Zoom? But Maria.
Thanks for your presentation, Patricia. I have a question. It's more a curiosity about the siliceous fraction. Did you compare with the siliceous plankton, or did you see just an increasement? Yeah, or something related?
So the question is if we compare with siliceous plankton?
Yes, diatoms or radiolarians or no?
We would like, but we didn't.
Thank you.
But this is not the, are you talking about the Mediterranean or the Pacific?
That case it would be or in the Pacific too. I suppose in the Pacific you have more siliceous fraction.
There are siliceous organisms. The Mediterranean a bit less.
Yeah, okay.
Any other question? In Zoom or no? Patricia, I have a question, sorry. I don't understand exactly what is the relationship with the nitrate changes and the CO2 changes that you present in a figure.
I mean, you mean this work that has been done on nitrate and this projection on nitrate?
Yeah.
Oh, it has to do with stratification again. So basically, when you have a warmer ocean, you stratify the ocean, so you have less capability of fertilizing the surface ocean, because these projections are for the upper 100 meters. Stratifications due to basically thermal stratification will impact nutrient concentration in the upper 100 meters, because you will have less mixing.
Okay. It's most a result of that stratification than the increase of the nutrient source, for example. Right?
I don't know.
It's more than certification. It's more a result of a stratification than the source, for example, of nutrients.
Sorry, I didn't understand.
The changes in nutrients, you say, is more than a stratification, and the changes in source from the earth, for example.
These are projections for the global ocean, so we're not really talking about coastal system here. It's more global ocean.
Okay, thank you.
It's more pelagic type of environment.
Okay, thank you very much.
Yeah.
No. Thank you, Patricia. Okay, our next talk is by Andrea Giulia Barzi. Okay, Andrea.
Thank you very much. So, hello everybody. I'm Andrea Giulia Barzi. I'm a PhD candidate from the University of Milano Bicocca, and I'm going to talk a little bit less of forums, I'm sorry, but I will mention them, I swear. And I'm going to talk about a geomorphological characterization of methane seeps present in the Colombian Caribbean. So it may happen that in the sub-bottom there is the presence of natural gas, and which is trapped in the sediments. And among these gases, methane is the most common one. And sometimes, due to some different processes, these fluids may escape into the marine environment, creating peculiar landforms on the seafloor. And among these landforms, we can find the pockmarks, which are concave crater-like depression, which form after the emission of these gases because of the collapsion of the sediments. So whenever we find this kind of morphology, we may have an indication of the presence of a past or present fluid flow system. But in general, up to now, there is a discrimination between neither the type of fluid nor their origin, but normally pockmarks are classified according to their morphology, as you can see here in this graph, in this image. So, the study area of this work is located in the Colombian Caribbean. Specifically, we are offshore in the Gulf of Morrosquillo. This is the study area, and we are located mostly closer to the continental margin of this area. And it's been known that since the 1970s that this area is maybe considered a gas province, mainly dominated by methane, which may have microbial or thermogenic origin. Nevertheless, this area is still understudied and there is little knowledge, which is why it's been chosen as a study area of this project, which is called methane seep hunting, which is a collaboration between several international universities led by the UPB, which is the Universidad Pontificia Bolivariana in Medellin, and some other Colombian partner. The main goal of this project is to develop a multi-scale and multi-method approach for detecting these seeps, so providing a characterization of the landforms and their current or past seepage activity. And so these are among the main goals of this project, and I'm gonna mainly focus on the third one because I will talk a little bit more about the geomorphological characterization of the landforms that we found in this area. So in May 2022, there was the first at-sea campaign where we performed a multi-beam survey collecting bathymetric, backscatter, and water column data. On the basis of the data collected during this first campaign and some other knowledge about the presence of oil leaks on the top of the surface in this area, there was the definition of many sampling sites. Indeed, in June 2022, there was the second at-sea campaign where we performed sub-bottom investigation, ROV investigation for ground truthing our data, plus box and pistol core for biological and sediment sampling. So, in general, the multi-beam data have been processed by using the QPS suite for analyzing the bathymetry, the backscatter, and the water column data. Moreover, the output of these analyses were then imported in ArcGIS Pro for performing some main terrain analysis and the mapping of the features. For the sub-bottom data, we use the SonarWiz for analyzing the data, and in general, all the data have been then imported in Fledermaus for having a better integration of all these multi-scale and multi-method analysis, and for a 3D visualization of the whole environment. As I said, the ROV data were used for ground truthing, and finally the box and pistol cores have been analyzed by other colleagues more expert than me in the field for the biological and the sediment analysis and characterization. So here you can see the bathymetry of our study area, which goes mainly from 40 up to 350 meters of water depth. We covered an area of about 220 square kilometers. And here you can see the backscatter of our data, where the black color means a lower response, so softer material, while the white means the presence of a more harder substrate. And here you can see all the sampling station that were performed. And in correspondence to these points, it was performed also the sub-bottom surveys for the investigation of the sub-seafloor. This is okay, it's not very visible, I'm sorry. This is should be a snap of the seismic data, where we can actually see some anomalies in the water column, which means that the possible presence of filtration in the marine environment. And finally, we analyzed the water column data collected during the multi-beam survey. And here you can see what we can actually see in the software when analyzing the data, meaning the evidence of seepages in the marine environment. And here you have a snap of what the integration of, in this case, of the bathymetry and the flares, which actually, and it's quite visible, the correspondence of these anomalies with the morphologies that we find in the seafloor. So as I said, later we put all our output in ArcGIS for performing some analysis, and in particular we derive some main terrain parameters such as the slope, aspect, curvature, BPI, roughness, and all these layers have been used for producing some species distribution modeling, especially for the foraminiferous and the macrofauna that were collected and characterized, and especially for those species that are SIP related. Moreover, I was interested to give it a try to do this kind of modeling also for the flares, so trying to predict the presence of the absence of methane emission using the same approach. So back again to our bathymetry, by using the Comma toolbox, which is a toolbox available for ArcGIS Pros, and you can download at this link, we were able to perform a semi-automatic mapping of the features characterizing this area. And here you can see the result of the mapping of only the negative morphologies, and in particular, so we are talking about 22,000 negative features were mapped, so it's a huge amount of features, and we are talking only about the negative ones. And here you can see some graphs showing basically their morphology, the elevation graphs. So we're talking about what we believe are pockmarks having a metric resolution. Sometimes we find bigger features from 20 to up to 60 meters of length and width, and sometimes we find also some smaller features. This is the result of the flare distribution modeling, where the red represents a higher probability of encountering SIPs, and the blue a lower probability. And here you have a snap of of this graph, because it's quite big, the area, so it's not very easy to understand everything. But here you can see that actually our mapping is not very visible, but our mapping quite correspond the results of the modeling. So what we can say, what we notice so far, is that in this area, which is closer to the slope, pockmarks have a more elongated shape, and this is maybe due to the action of the bottom currents that may affect the morphology of this kind of landforms. But in general, we find basically all around the area this sort of situations. So a major pockmark, like a normal pockmark, so a little bit bigger, clustered with other smaller features, which are classified as unit pockmarks. And here's an example, but we can see it also here. Here is a major cluster. So in general, we were able to basically recognize all the morphologies that have been already described in literature. Like sometimes unique pockmarks only, sometimes normal pockmarks associated to unique pockmark, or like even by themselves. Moreover, if we have a look on the backscatter, we are also able to recognize some hide pockmark. In this case, we are talking about pockmarks which show a higher reflectivity, a higher backscatter, probably due to the fact that we have carbonate precipitation due to microbial activity. And this is quite an interesting thing, because I would like to actually classify all my pockmarks according to the signal of the backscatter, in order to have a better understanding of where we can still have seepages, and in order to discriminate if the fluxes are still active or not. So, okay, so, and this is another peculiar area that I'm interested about, because here in this area we can see a lower backscatter, so soft sediment. If we zoom in, we can actually see that there are like some other peculiar morphologies, but in this case we are talking about positive morphologies. So we believe these are mud volcanoes related to the presence of what is now, I mean, here we didn't find any evidence of fluxes of methane, so we believe they are landform related to a past seepages, and my intention would be also to try to map all these positive features presented in the study area. So to conclude the resume a little bit, we were able to find about 23,000 pockmarks, and we were able to actually see different morphologies. But as I was saying, the mapping is still in progress. I would like to revise all the pockmarks that have been delineated, because I noticed there are some missing features. Some of other morphology have not been mapped correctly, probably because I need to play a little bit more with the parameters of the tools. And as I was saying, I would also try to characterize the positive feature to have a better understanding of all this area. And in general, I believe this is a useful thing, because pockmarks are associated with methane flux. So we have a passage from the lithosphere to the hydrosphere, and sometimes even to the atmosphere of this of methane. And since methane is a potent greenhouse gases, it's important to take into consideration the carbonate budget also related to this kind of emissions. So as you notice, we are really investigating a pockmark field, a huge field, really geomorphologically important, which actually delineate the presence of a past or sometimes even present fluid flow system. And this is also it has also its relevance according to a hazard point of view, because we know that this kind of morphologies are also related to instability of the seafloor. So there are a lot of future things that that we are doing in this project, because it's a very interdisciplinary project, from biological sampling, sediment sampling, and so far the thing that I would like to do is to integrate some seismic data that have been they are under investigation now, and to integrate the results of the seismic data with my mapping, in order to better understand all the story of this area, and specifically the origin of the fluid flow system. And with this, I'm concluding. I would like to thank the Inqua Mare organization and everybody here for listening to my presentation, and in particular to OGS, because it's the reason why I was able to come in present here. So thank you very much to everybody.
Any questions? Andrea? Okay.
Hi, Julia. Thanks a lot for your presentation. It was really, really nice. I was wondering whether you were able to sample the mud breccia, and if you are...
Sorry,
the mud breccia, the mud coming out from the mud volcanoes.
we have some samples in the Mare volcanoes that I show, we have no station, I believe, because it wasn't really visible at the beginning and the sampling station, that there was this kind of morphology. So we don't have a station directly there, but we found some other similar morphologies around the area. The point is that they have a different backscatter, so I believe it's going to be a different morphology, like some not really related. But I mean, this is quite interesting, and I hope that there will be like other investigation in the area, especially the point of view, have a better understanding also of that.
Thanks a lot. And another question, did you find any chemosynthetic fauna?
Yes, all the programs and the macrofauna that were actually studying were used for the species there, or methane-related species. I cannot tell you the name of the species because it's not really my field, but I can swear they are methane-related. That's why it's I think it's good to the integration of this kind of knowledge, what we can actually see other method on the sea. There is like a great ecology, everything.
Thank you very much.
Renata from OGS.
Hello.
Hello. Have you surveyed with the underwater camera?
We have some yes,
images.
We use the ROV for the ground truthing, and we have some videos from mainly where we collect the sediments, where we collect the sampling, biological and sediment. And yes, sometimes we can observe a carbonate crust. We can see the bubbles coming out from the seafloor. So we have evidence sea occurring.
Okay.
But the point is that it's like a very area, and we don't have strategies all around. Like sometimes they have active, but are related to past activity. It's complicated, fascinating.
Yeah, it would be nice to have a long course in order to understand the evolution of the system.
Absolutely.
Yeah.
I agree.
So sorry, another question that just came into my mind. So you said that there are the sea page are not all over the place. So do you think they are related to any like tectonic feature of the?
Of course,
Okay.
yeah, I do believe this is the main reason. But yeah, the point is that that's why I'm integrating the seismic data in order to try to understand what's the origin of the fluid. So why we may find the sea area, but not in this area. Try to better understand what's the story.
Any other question? Well, thank you very much, Andre.
Thank you.
Okay, thank you, everyone. Now we have the coffee break. We can have to return at 10:30, and see you.
Olá, boa tarde, bom dia. Eu gostaria de testar também. Helenice, você está aí, querida? Sim, estou. Olá, vamos ver aqui. Eu estou entrando também. Vamos testar? Pode ver. E a minha câmera, tá vendo? Tá me vendo? 33. Tá quente aqui. Tá quente, né? Aqui tá, aí tá 33, aqui tá 32. Tá quente também aqui. A Anne disse que lá tá 13 negativo. Ela chegou quando? Oi? Ela
Não,
chegou quando?
ela não tá aqui não, ela tá lá.
Achei que você estava com o computador dela, que ela estava aí
É,
do teu
é o
lado.
computador velho que ficou em casa.
Que bom, hein?
E o meu é mais velho que o dela. E deu...
Hola, Elenice.
Olá, Dorothy.
Hi, it's Karen. Can you hear me?
Hi. Yes, very well. And you?
Yes, I can hear you.
Okay.
Okay. Good
I
morning.
test already, but the presentation, I think it's okay.
Yeah, it's perfect. We can see it perfectly. So we are still having the coffee break, but like in 9 minutes, we'll be back.
That's okay. I just try already to see it's
Perfect.
okay.
Perfect. Thank you.
Pronto, tô de volta. Deixa eu ver. Aí, pronto.
Eu não vou mais mexer.
Não mexe mais, deixa aí. Meu também. O Rafa arrumou para mim de manhã e eu não mexi mais nesse computador. Mas aí ficou aquela tela laranja. Ah, que bonito que colocaram ali. Olha que chique, professora. Que linda.
E essa foto foi no embarque. Eu falo com você depois.
Ah, é? Ficou bonita. Foi do Iodipi, não?
Não, foi do Vital da Oliveira o ano passado.
Ficou bonita. Lá no Iodipi eles fazem também a foto bonita da gente. A minha até hoje é aquela.
Eles conseguem, né?
É. Que mais? E o Val tá aí?
Agora ele tá sempre, aposentou, tá sempre em casa.
Que bom, né?
Pelo menos eu não fiquei sozinha, né? Antes se foi, ele veio.
Se deu bem. E a Anne tem quantos anos mais lá que ela tem pra ficar?
Mais um ano e um pouco. Se ela fizer o estágio, 1 ano e meio. Se não fizer estágio, 1 ano. Exatamente se consegue o estágio.
Ela vai fazer estágio, né?
Ela disse que aí vai para um escritório, aí tem experiência diferente, né?
Ah, que legal, que bom. Ela tá gostando de ir lá, Helenice?
Diz que é muito boa a universidade, tá gostando demais mesmo.
Que bom.
Mas agora.
Não. E escuta, e o hotel que não quer me devolver o dinheiro? Olha que sacanagem, Helenice. Nossa.
Eu acho que ela não vai devolver, não.
Ah,
Se
óbvio
bem
que
que a culpa não foi sua, né? A culpa foi do.
não, eu tenho um papel de cancelamento, né, que eu mandei para eles e tal, mas eu vou conversar com elas, né, porque se eu receber o prêmio, né, mesmo, aí tudo bem, pago, tudo bem, né, mas, poxa, nossa, que desespero. A passagem vão devolver em 60 dias, né, Denise? Gente, mas tudo bem, vai. Mas vão devolver, eu consegui o ressarcimento e eu tenho que te devolver, né?
Se conseguir, né? Se não, paciência. Bora ver.
Querida, mas assim, eu vou fazer de tudo, porque são US$ 300, né? 280 e tal, que eu já paguei. Mas desesperante, né? Você viu o que aconteceu? O que aconteceu? Por quê? O que foi isso?
A aeronáutica que deu pane, né?
Foi uma aeronave aí qualquer que deu problema e eles pegaram de circulação 177 aviões, né? E a Copa ficou com 4 desses que faziam essa linha retidos. E aí foi sábado. Então, eles sábado passaram os passageiros de sábado a domingo, de domingo para segunda, entendeu? Aí quando eu fui já estava muita gente. Fui lá pegar uma aguinha.
Vamos sair agora.
Vai ser agora?
Não, eu almocei logo.
Meu Deus do céu, muito nervoso. Deixa eu fechar.
A tua mãe e as gurias, as meninas.
Então, bem, a minha mãe está indo para ginástica daqui a pouquinho e as meninas estão lá embaixo, na piscina. Aí eu vou passar o ano todo, até o final do mês, aqui com a minha mãe, né? E aí vou embora, né? Porque 6 meses tem meu pai chato, né? Escreve.
Isso mesmo. Para ela, principalmente.
Mas também ela tá bem, porque ele tava ruimzinho, né, querida? Queria tanto.
Thank you very much for being here. Our next presenter is Helenice Vital. Helenice is from
Yes. Can you hold me?
Helenice is from the Universidade Federal do Rio Grande do Norte. Helenice Vital works at the Universidade Federal do Rio Grande do Norte, Brazil, at the Department of Geology, where she has been full professor since 2010. Her expertise includes seabed mapping, sedimentology, marine geophysics, petroleum geology, stratigraphic correlation, and oceanography. Since 1988, she has been participating in many research crews and expeditions on shelf and slope. In 2023, she was awarded with the Eugene Delay Fund Medal during the International Union of Geodesy and Geophysics in 2023 General Assembly. Okay, thank you very much, Helenice.
Hi. The Lord me. Hi. Can you hold me? Good morning, everybody. I thank you for the invitation, especially Kari and Caterina and all the Inqua Mare group. I will speak a little about on the Brazilian tropical shelf, just an overview. And we could split the Brazilian tropical shelf into.
Sorry, Helenice, just give us 1 second, please.
Hi. Could you hold me?
Sorry, give us a minute.
Can you see the PowerPoint?
Right now, it's okay.
Yes. Okay. So the Brazilian tropical margin is split into great areas: the Brazilian equatorial margin to the north and the Brazilian eastern margin to the east. This is split by the Mare plateau, and the main difference with them is while the northern Brazilian shelf is most terrigenous, the northeast Brazilian shelf is most carbonatic. And on the North Shelf, we have the predominance of tides, waves, and currents. In the Northeast, most of the waves and currents. And siliciclastic carbonates on the Northeast, and most siliciclastic on the Northern. And the geological history of the area, like a special route. And we can see to the right the geology, and we show the two main basins, the Amazon Basin and the São Francisco Basin. The Amazon Basin is providing the sediment for this North Shelf, and many other small basins to the Northeast Shelf. Climate also is important for this area, while the area for the Amazon Basin. The climatological normals show average annual rainfall from more than 1,800 millimeters. It can reach until 3,400 millimeters, while the Northeast sector is little than 1,600 millimeters. Most of them little than 600 millimeters. And we can see the red arrows in the picture show the main sediment way. The bigger the red arrows, the more sediment. And it's clear that Amazon contributes with much more sediments than the small rivers on the Northeast. In the other picture, you can have a look on the range, the tidal range. And most of the Northeast is mesotidal, from 2-3 meters until 5 meters height. But the north, they can reach a much more special, close 8. And these characteristics, we can divide this shelf in 3 main areas on the coast. We have the deltaic coast, the sediment-starved coast, and the tidal environment in the Amazons. And in this tidal environment is plenty of mangroves, that is mixed in green. And we have mesotidal reefs along all the coast, which you can see in pink. Then we can see that the Amazon special system is the most important in the Brazilian tropical north, and the Amazon, the source of the Amazon River is on the Andes, and when they came to the mouth of the Atlantic Ocean, is more than 6,000 kilometers away, and in the Amazon system is large. Most of the Americas water sediment index station is also a natural place yet. They have some deforestation, but not so planned. While in the northeast shelf, there are many others small bases, especially the San Francisco's, which you see in the pictures. The source of the San Francisco is in the central plateau, and when it came to the Atlantic Ocean, it's plenty of white sands or siliciclastic sands, and the sediment plume is much smaller than the Amazon. And I will show some illustrations from the North Shelf, Brazilian North area. And we can see in the satellite images, which is in brown, is the sediment plume from the Amazon. And the picture show how is the coast and the shallow shelf close to the Amazons, plenty of mud sediments. The storing process in the shelf, you can see we can show the importance of the tidal fluctuations. During the spring tides, this is very energetic, and have mixed water column and sand at the bed, while during the neap tides, this is less energetic, and mud settles near bed in the turbid mass. This creates a fluid mud bigger than 10 grams per liter. Then the X ray, you can see the interbed sands and mud creates from the tide lights. On the shelf, the farm are with apparent, and then we can see dominant figure of the Amazon and have modern sediment. This can reach the continental shelf. On the idyllic sands, we can see on the border of the shelf. Mesophytic reefs also are present on the border of the shelf. Proximal to the star, we can see a picture from the Amazon River to the Orinoco River. Then the Amazon sediment can attention to the Orinoco and beyond, and the mud capes extend along the coast. In low stand of the sea, then the Amazon sediments pass through the Amazon canyon until the fund. In this case, the turbid currents on our view the Amazon funds and complex. Some last which you can see from the Amazon source to sink system is about the time of transfers, the peak of sediment level when the water below levee increases, and much sediment supplies to energetic ocean conditions, and then is transported for set in the shoreline. A couple of processes overlapping transition of fluvial and tidal process cause a central tide river fluid plain to be effective sediment track. sediments, progressive sort libraries only finds fracture the shelf, allowing flood mud to dominate sediment transport. On the northeast shelf, we see 4 different sections. See the diversity of geomorphic features. And in this picture, you can see in A, as a relief image. In the picture B, the sediment distributions, where the yellow are siliciclastic, blue the bioclastic, and between them the mixed sediments. Along this northeast coast, we'll see a beach rock chain along the 25 to 30 meter depth. We can trace this beach rock chain along all this northeast coast. Also typical for this area are the coral reefs, the mesophotic reefs. You can see 3 main pictures there. In the Abrolhos on the Espírito Santo, which is on the south, is the Aço reefs. They're in the Pernambuco reefs. They are most of them along the outer shelf. In a picture about the Espírito Santo in the Abrolhos, is where you have the one of extended the extension of the shelf on the northeast. And in the picture where you can see the bathymetric map from this area, the red one close to the coast, and the blue and the shelf break. And you can see the sedimentary faces map. The red colors show the extent of the hodolites present in this area. And you can see the other pictures, the relief attributes, and the different bottom types. On the bottom, you can see the size of the valleys on the Guarapari, Espírito Santo. And some images of the hodolite bottles from this area. And close to Salvador in Bahia is where we have the narrowest shelf, maximum 9 kilometers from the coast. You can see also some bathymetric map. In A, you can see the grain sizes change from sandy to gravel and mud. And in B, we can see the shell habitats. And in this image from the fragment of coralline algae, which is the major component of the sediment cover, the hard bottom habitat in this area. And the picture from the Pernambuco shelf, also you can see the digital bathymetric model, benthic structures and geomorphic features, you can see. And also the plateau multi-beam bathymetry. In the bottom picture, you can see acoustic backscattering. Also the presence of incised valleys on the slope and the presence of benthic structures. Beyond the Rio Grande Norte shelf is in the corner of Brazil. You can see the top the digital terrain model and multi-beam bathymetry to the upper slope. And you can see the print of canyons inside on the slope. The sedimentary faces show that close to the coast we have siliciclastic sands, while in the outer shelf most are bioclastic, and between them the mixed sediment. The black line shows this line of beach rocks along the 25 meters deep. And you can also see the average density of the most abundant taxons in these areas on rain and the dry seasons. amount of sediments. It's easy to see this area in satellite images. And you see in A and Landsat images where you can see different features on the shelf. And in B you can see a battery model with single beam. And then it's easy to see the difference where are the inner shelf, and outer shelf. And you can see the two inside the valley, and Aço Piranhas River and Apodimosoro rivers. In this area you can see very large public dune fields that can be seen very well from satellite images. Small dunes are also present on the shelf on satellite images. It's too small to see the scale, but when you use the side-scan sonar, they are there, and with 2 to 3 meter wide and up to 0.5 meters height. Most of this materials are composed of biosilice glass and the silice bioclastic sands. A vision of the inside the valley on top of this area. And you can see the limit between the Pleistocene and the Holocene, which you call the horizon one. And you can see on the base of the valley. And this marks the boundary between the Holocene transgressive marine sediments which fill the valley and the underlying Pleistocene and the Holocene non-marine deposits. And on the slope, a split of canyons, I can see in these pictures with multi-beam mapping. And here is also in Rio Grande do Norte, but on the east side, in front of Natal, you can see this canyon, and how is this? Well, you can see in seismic sections with shape systems. And you can see a structural high in the distal part of the canyon, and the deposits of unconsolidated sediments on the paleotrainer borders derived from gravity flows. And some pictures of these sediments from these areas. We can see mud sediments only close to river system where we have inside the valley. And then these mud sediments are filling the size the valley with the silice class close to the coast and in direction to the shelf, outer shelf, it became more carbonatics. Most of the sediments are sands and gravels went off bioclastics. The algae are the most principal sediment in this area. Then you have this from red algae, green algae, and also the mollusks. You can see some bivalves or gastropods. And also the foraminifers, both planktonics and planktonics. And in this picture you can see the reefs on this area. In the middle we have a profile with shape system. And you can see the height on these small pond reefs. And on the bottom we have a side-scan sonar profile. Show that in the middle, on the side of the valley, you can see biosilice plastic sands and also bioclastic sands in the reefs. The human uses in these areas, the major human uses is for oil and gas extraction, fish, tourism, silice classic and bioplastic aggregates extraction. In the Rio Grande do Norte shelf, the salt extraction in shrimp farms is very intensive. And in this area it also holds a very high potential the south and the abroad shelves, Uton is present the most extension of all the light beds on the entire shelf. Upwell has also been documented the numbers of canids heads in this region. You have some pictures from the Rio Grande do Norte shelf showing this man uses we have quotation for the pictures on the middle where you can see exploration for the shelf, which is in blue, light blue. Then we have exploration of oil gas, production of oil gas, and then place for offshore eolic projects. So this is a very small look about this area. I thank you for the attention. We'll be here for questions which if you had. Thank you too much.
Thank you. Thank you very much, Helenis. Any questions?
Good morning, Helenis. Thank you for your presentation. It's Karen here. So I would have two questions for you. The first question is, given that the shelf is, Brazilian shelf is so long, if there are any studies on the distribution of clay minerals and if they change a lot, if the distribution of different clay minerals change along the shelf. And the second question is, you have shown how much the shelf can be exploited by society. And I was wondering how you as Brazilian researcher can speak to politicians and the government in order to, let's say, regulate the exploitation of the shelf. Thank you.
Thank you for the question. The first one about the clays. We have most studies which we have on the clays are on the North Shelf because of the Amazon River. And for sure that we have many studies. Most of the clays are kaolinite, morronite, or smectite. In most of them, the source are the Andes. But for the other place for the Northeast, because the rivers are so small, the amount of clays which have in this area is not so high, only close to the river mouths. And about the use and what we can do with the policy organization about this is really a problem because we know so many about this area which I show is about 3,000 kilometers of extension. And what we know about is too little for this kind of exploration which they want to do, or they are doing. The oil and gas is already played, but the offshore wind farms, no one are yet beginning. They speak a lot about this, but the problem is really we don't know enough about the shelf to begin these studies. And we hope that because of this, the government must invest in also the firms which want to work there. They need to do this before.
Thank you very much. Thank you.
Any other question? Zoom or?
Hello, Helenis. I'm Caterina Morigi from Pisa. Hi. Thank you.
Hi, Caterina.
Hi. Thank you for your nice and exhaustive explanation about the shelf of Brazil. I have a question about the mesophotic reefs. I didn't understand at which depth they live and if there are already studies that have investigate this environment, this type of reefs, of coral.
Good question. Thanks, Catherine. We know that they are there, but small studies, most of them are close to the border between shelf and slope, but because it's more difficult to us to go there. And we know there's in some place, but when you go there, we find them. And that means they must be there, but we have no study in all the shelf.
Okay.
And we need more studies.
Okay, so thank you. It's something to investigate. So,
Yes.
Okay, thank you.
A plan of things to investigate.
Any other question? No? Okay. Thank you very much, Helenis.
Thank you for the invitation.
Thank you. Our next presenter is César Sequeira Peraza from the Universidad de Costa Rica, Escuela Centroamericana de Geología.
Hello, everyone. Good morning. Okay, so I'm gonna switch to the Northern Hemisphere and talk a little bit about the Grand Banks earthquake and tsunami that happened in 1929. And I'm gonna switch more towards deformation of much older sediments instead of, like Holocene or even Pleistocene sediments, and looking at seismic reflection data to see what we can learn from the deformation associated from this earthquake, specifically if we can see the source. And to do this, I'm gonna ask myself these leading questions. One is if there is any subsurface evidence associated to the earthquake, and if so, what's the location, what's the geometry, and what's the timing of this deformation? And finally, if the seismic reflection that I'm looking at is reliable to tell this. So, just to give us an overview of this place, we are on the northeastern margin of North America, specifically on eastern Canada, the Maritimes. We have the Scotian Shelf right here. We have the Laurentian Channel here, and we have the star that marks the epicenter of the 1929 earthquake. We also have the Grand Banks here, which is a very wide part of the continental shelf. And for those of you who are fans of Titanic or Celine Dion, this is the place where the Titanic sank, just to give you a reference for it. We also have the Mid-Atlantic Ridge right here that separates the North American plate from the Eurasian plate and the African plate to the south. If we throw the tectonic setting on top of this map, we have a little more complicated setting. Starting from older to younger, we have the prairie rocks and older that are part of a Paleozoic convergent margin. We have the Appalachian Range here, and lots of reverse low-angle faults that later became reactivated as normal faults during rifting. We know that this was ongoing around the late Triassic. We don't know exactly where it started, maybe in the middle Triassic or early Triassic, but it was underway in the late Triassic. Then breakup, or the first oceanic crust, began. Diachronously from south to north, it started off in the early Jurassic in the southern part of the margin, all the way up to early Cretaceous in the northern segment right here, and even in the Paleogene up in Greenland and northern Canada. Eventually, we have the development of the continental margin and what we call the passive margin of eastern North America. And I quote passive because it's not as passive as we think it is. Much later in the geologic history, we have the Pleistocene glaciations. And if we look at the last glacial maxima, the Laurentide ice sheet reach the edge of the shelf all the way here, and we have flowing ice where the current Laurentian channel is. And again, the earthquake epicenter is around here, and that's very important to point out. So what happened in modern history? So in 1929, there was a magnitude 7.2 earthquake off the Laurentian channel. This earthquake triggered a slump and turbidity current right off the slope of this margin, and this slump suctioned water and then created a tsunami that reached as far as Portugal to the east and South Carolina to the south. So let's talk about the earthquake. It happened on November 18 in 1929. It was in the late afternoon. It was already dark in Canada, 5:02 p.m. The magnitude was 7.2, but it was felt as far south as New York and Toronto. The local intensity around St. John's, Newfoundland, or Prince Edward Island was around 6.7 in the Mercalli intensity scale. Then let's talk about the slumps and turbidity currents. Back then, there were telegraph cables. Well, I guess they still exist there. But because of this event, this turbidity current, there was a breakage of the cables and loss of communication between within Canada and between America and Europe. Some of these cables broke up instantly during the earthquake, but some of them broke off at different times. This was used by previous scientists to calculate the velocity of the current, which was estimated at up to 19 meters per second, which is around 68 kilometers per hour. And later, with side-scan sonar imagery, people were able to see the evidence of scarring and slumping and deposits along the slope of these plates. So it was very well recorded. This was the first recorded turbidity current in history. So it was great for us, right? But not so great for the local people in 1929. So the tsunami was approximately 3 to 7 meters high in the wider base, but it was up to 13 meters high in the narrower passages. Obviously, there was widespread destruction, especially in the southern Burin Peninsula. Obviously, flooding, wreckage of houses, and people drowned. 27 people drowned, plus one more girl who died eventually from the injuries. So what I'm gonna do is looking at this seismic data that's available on the edge of the shelf and see what the formation there is, okay? And then I'm gonna evaluate this data with interval velocities and see if this data is reliable. So this is a generalized stratigraphic column of this area. I'm gonna focus on reflections on the seismic data that are on the upper shelf or topmost shelf, relatively speaking, because it starts in the early Cretaceous and above. I'm gonna focus on nonconformities and high amplitude reflections that can be traced laterally. So this is the edge of the Laurentian channel. This is the available seismic data. As you can see, there is a lot of exploration here by the Canadian government and private companies. And I'm gonna focus on this spot right here. These are the key seismic profiles that I'm gonna show for 1, 6, 7, and 2. And I want to add this gray northwest trending line. That's a model of the rupture that Alison Bent proposed in 1995, which is a left lateral fault with some reverse component. And this is very important. So if we look at the shorter profiles, 6 and 7, what I found is some offset of the reflections that I focused on. The interpreted image shows reverse offset of a plane at the top and normal offsets at the bottom of the same plane, which is kind of weird, right? We would expect like the same offset for the same plane, but in structural geology, that's common depending on the geometry of the structures. Profile 7, it's a similar situation, but not as clear as profile 6, but again, we have reverse component on top and normal components at the bottom. If we take a look at the longer profiles, east-west trending profile 1, it's more complex. We can see from bottom to top, normal faults here, another reverse fault here. We see some folding, apparent folds. I'm going to point that out. And then paleo channels of different ages, Oligocene paleo channels and even Pleistocene channels, which is expected because sea level was lower and erosion was more intense on the upper shelf. A little bit to the south, profile 2 shows the same situation, more paleo channels plus some structural highs that coincide with the location and reverse geometry of the upper channels that sit right on this part of the profile. When we look at the structure contour maps of 3 different horizons, this is the early Cretaceous Avalon conformity. We can see that there is a structural northwest trending high, and then a more focused high here. If we look up to the Wyandotte formation, the top Wyandotte formation, we can see that there's still the same high showing up on this formation right here, plus another Oligocene channel that sits next to the apparent high. And then moving up to more or less the Pleistocene, we can see a more flat horizon plus a Pleistocene channel right there. When we look at the 3 structure contour maps interpreted plus the northwest trending fault from Allison Bend, we can see that there is some correspondence on the trend of the apparent high and the channels. The high more or less resembles the geometry of the Pleistocene channel, which is kind of problematic because it tells us that there might be some artifacts in the seismic data. However, there is an Oligocene channel that sits next to the apparent high. Does that mean that there was a structural high, a real one, that's blocking the flow of water and then creating or locating the channel right here? That's what I want to evaluate. Besides, we also see the reverse faults right here, plus some other normal faults that are related more to rifting. So, to evaluate this reliability of the data, we have to look at the way we process seismic data. So remember, when we look at seismic profiles, we're looking in time space, not actual depth. So it depends on the velocity model of the data, the geometry that we're going to see on the seismic profile. So if we have equal velocities adjacent to the channel, we'll see no change in the underlying geometry when we get the seismic line. But if the channel has a higher velocity, the underlying reflections are going to show a pull-up because seismic waves travel faster and arrive first compared to the paths around the channel. So it's an artifact, right? It's not a real fault. It's just an artifact of the processing. And if the channel has a lower velocity than the surroundings, there's going to be a pushdown. It's the opposite, okay? So when I looked at the stacking velocities in the velocity model for the lines and created or calculated interval velocities for my interpretation, I see that the Pleistocene channel has slightly higher velocities than the surrounding strata. Okay, we can see 2.5 compared to 2.2. When I converted that to depth, the seismic high didn't completely flatten out. We still have that little bump there. Here we have a slightly low, okay? Besides, we have the reverse component here that's not gonna get flattened out because it's completely separated reflections. So that's not gonna get corrected at all. Considering the uncertainties of the seismic or the velocity intervals, there is a range of possibilities when we combine the velocities of the adjacent strata and the velocities of the paleo channel. So to recreate the velocity high or the structural high that I get in the lines, I need a combination along this line. Okay? Anything higher than this is going to create a pull-up that's smaller than the apparent height that we see right now, and anything below that is going to be larger. Okay? So for the data that I have, this is where the calculation falls. It falls within the range where the pull-up exists, but it's not enough to completely flatten that out. So we still get some differential height, 70 meters of height. Okay, that means we need approximately 350 Grand Banks earthquake to produce that uplift. So, in conclusion, can we see the source? No, because based on the seismic or the seismological data, it's 30 kilometers depth, so there's no way we're going to see that source. But we see that there is evidence of much shallower deformation on the overlying sediments. They have some reverse component. They also have normal components. So that means that it might be strike slip faulting. That's the one deformation that's less complicated to create that kind of offset at the same time, which coincides with Allison Bent's model for strike slip faulting. And the seismic reflection data shows velocity artifacts for sure. So we have to use it cautiously. So thank you very much, and I'm happy to take your questions.
Okay, any questions?
Thank you, Mark Furs from the University Centre in Svalbard here. Given its location beneath what was once a pretty major ice stream draining the Laurentide ice sheet, would there be any issues related to ice unloading, isostatic readjustment being accommodated by fault reactivation along that system?
Yeah, certainly, yeah, there could be some isostatic rebound of the continental crust that's sitting there, but the focal mechanism doesn't explain, a vertical movement. Instead, it has some right lateral or horizontal component. That's more in line with current stress states in the northeastern part of North America. So the current horizontal shortening goes to the northeast. Okay, besides, we also have, I forgot to mention, but we have we have the New England fracture zone. We have the Newfoundland fracture zone that has a similar trend. So my guess is that there could be some influence of an initial extension of that fracture zone into the continental crust that created a weak zone for further reactivation.
Thank you.
Any other questions?
Thank you very much. Mine's just a curiosity because I'm very ignorant about these things, but are there been any other major event, earthquakes before or after the 1929?
So not on Eastern Canada. There is seismicity on this part, as we can see here, but these events are like 4 point something. However, on Eastern North America, there is seismicity. In 2011, there was a 5.7 magnitude earthquake in Virginia, and there was also the famous New Madrid earthquakes in the winter of 1811 and 12 that were between 7 and 8 magnitude momentum, and that happened like in southern U.S. So the margin is active; it moves. That's why I said it's not as passive as we think it is. Like, it didn't break up at the end of, Pangea and stayed like that. No, it's still moving, but not as aggressively as a convergent margin.
Thank you.
All right. Any other?
Hi, thank you for the presentation. This is just a curiosity. There are other events that create turbidity current that are studied as this one, because this is really an example. When I explain turbidity current, I put this example to the students. Are there any other event like that that create turbidity currents?
Well, I haven't looked at it, at least on the eastern margin of North America, but certainly there are like in convergent margins that are more, more frequent.
Okay, not here, not in the Atlantic.
Yeah, not here.
Okay.
This margin, like in terms of instability of the slope, is it's relatively stable.
Yes.
Yeah, this was an extraordinary event. Supposedly, that the interval occurrence of these earthquakes are about 500. So yeah, this was extraordinary event. We had the cables right where we needed them.
Yeah,
and that's when we saw
this
that.
is the reason to that is ETL. Thank you.
Okay, thank you. From Zoom or anybody? No.
Thank you, Cesar, for the presentation. So I have a question. Maybe it's not really a good one, but you were talking about, of course, the turbidity current. I was wondering if the instability of the slope beside the earthquake, of course, was given more by the liquefaction of the sediments, or if there were some methane source.
It was liquefaction of the slope, yeah. And then the current was like mostly muddy sediments, but it has a lot of pebbles within that were sitting on top of the shelf, and that's a result of the glacial deposit at the very edge of the slope, and that's what actually creates the high velocity in the channel, because it's poorly sorted, so the pores are very tiny, so waves travel faster.
Thank you very much.
You're welcome.
Okay, any other? No. Thank you very much, Cesar.
Thank you.
Okay, now we have the lunch time, and we have to return at 1 p.m. Any announcement?
Just thank you, Eddie, for being this a chair for us. And remember, we stop a little bit moment outside to make the group photo. Okay? Yes. Okay. Thank you. And we will be back at 1. Okay. Thank you.